So we spent some time recently unpacking The Productive Edge, that fascinating piece by Carol Berkovec, especially its implications for how we think about large language models. And as luck would have it, he's just published a brand new article, Every Bit Matters When Physics Meets Meaning.
It does feel like a very natural next step to take. We were looking at emergence and surprise in AI, right? And this one feels much broader. Like, how does what we do digitally actually have a real impact in the world? And how do we connect that to meaning?
Exactly. I mean, the opening question Berkovec poses is this: how do these tiny little digital bits, how do they actually lead to big changes in the physical world? And then he pushes it even further, like how do we bridge this gap between the physics of information and the meaning that we humans attach to it? We'll be primarily working with Every Bit Matters for this deep dive, but I think it makes sense to bring back some of the core ideas from The Productive Edge and see how they connect.
Sounds good.
So our mission today is to try and understand this whole interplay between information, physics, and meaning. And then what does this mean for understanding things like AI and the world around us?
Big questions.
Big questions.
Well, Berkovec begins by emphasizing something quite fundamental. Information is physical. He attributes this insight to Rolf Landauer, and it's a very crucial starting point.
Definitely. And he uses some pretty compelling examples to bring this point home. Things like the movements of electrons in circuits, the constant hum from server farms, and even the tiny thermal changes that happen with every single mouse click.
Right, and these are not abstract events. These are physical manifestations of information being processed and stored.
But what I found really thought-provoking was how he takes this even further. He shows how just one little bit of information, in the right context, can actually set off massive physical events, like starting an aircraft engine or shutting down a power plant, or even making someone laugh. That one little bit flipped in the right way carries real weight in the world. But then he introduces this paradox. He says, from a purely physics standpoint, two books, let's say the Bible and Mein Kampf,
Okay.
physically, they're very similar, just different arrangements of ink on paper. But obviously the impact they've had on human history and the meaning we derive from them are vastly different.
Yeah.
And he makes a similar point with GPS coordinates. A tiny difference in the digital code can send a self-driving car to completely different locations with potentially, disastrous consequences.
Yeah. So this leads to this really important question. What's the mechanism that takes these physically similar bits and turns them into such different outcome in the real world? And I guess even more importantly, how do they become imbued with such different meanings? And this is the big question Berkovec's trying to grapple with.
Right, and his first move is to lay out 5 interconnected theorems. His first one, intentionality demands memory. And he's quickly point out that he's using intentionality in a broad sense to refer to goal-oriented behavior or function. So what's that essential connection he sees between intentionality and memory?
Well, he argues that for any system to show goal-directed behavior, it has to have some kind of memory. This memory allows it to select actions based on those goals and to keep doing those actions over time. Without memory, any action would just be a reaction to whatever's happening right now. There'd be no lasting direction towards any particular outcome.
That's a good point. He uses this really helpful example of a robot vacuum cleaner. If it has no memory, it just moves around randomly. But if it has memory, it can actually intentionally go to the areas that need cleaning because it remembers where it's been and what still needs to be done.
Right.
And even a simple thermostat, you can think of it as remembering its target temperature and then acting to keep the room at that temperature.
So in this sense, memory is like the informational bridge that lets systems pursue goals with some degree of persistence. Then he moves on to his second theorem. Memory is hierarchical.
Right, let's dive into that one. What he's saying here is that if a complex system, like a human brain or an AI, shows memory at a high level, then some of its smaller parts, maybe even down to the quantum level, must also have memory-like properties.
The idea is that for something to be stable at a big level, like a long-term memory, the information had to be stored reliably at more fundamental levels too.
Interesting. He gives some pretty wild examples here, like immune cells use CRISPR sequences as a kind of genetic memory of past infections. And he talks about that fascinating 2007 research on photosynthesis, where they found evidence that quantum coherence might allow these little light-harvesting complexes to explore different energy pathways simultaneously, essentially remembering the most efficient route. What really stands out to you about that connection?
Well, I think what's super interesting is that it suggests there might be a universal principle of memory at play. Like any system, big or small, that can act with intention needs some way of holding onto its past to guide its future actions. And that leads us straight to his third theorem, no information without matter.
Right, this one seems pretty intuitive. The idea is that information can't exist in some abstract void. It always needs a physical something to be stored on and to be kept stable.
Exactly. Berkovec argues that storing information requires stable physical patterns. And these patterns can only exist if there's some physical structure to hold them, whether that's made of matter or energy. Think about it. Digital texts need devices to exist on. DNA physically encodes genetic information, and even the information processed in our brains is carried by electrical signals in neurons.
And he brings in this concept called the Bekenstein bound, which basically puts a limit on how much information you can pack into a given amount of matter. It's like a fundamental interconnectedness.
Yeah, it's fascinating. And then he flips this idea on its head with his fourth theorem. No matter without information, this one might seem a little less obvious at first.
Yeah, I mean, if you look at a rock, it just seems like a bunch of minerals. Where's the information there?
Well, Berkovec says that all matter actually contains information in its structure and organization. The way the atoms and molecules are arranged, that's an informational pattern. So a rock, even a rock, holds information about its geological history, how it was formed. DNA sequences carry the information for an organism of development, and even light carries information about the stars it came from.
So it's like a duality then. Information needs matter to exist, but matter also has information built into it. They're not the same thing, but they're completely dependent on each other. It's like two sides of the same coin.
Exactly. They offer different ways of describing the universe. Matter is about the tangible energy-bound processes, while information is about the underlying patterns and organization. And this brings us to his fifth theorem. Information processing is physical.
Right, which makes perfect sense if we consider everything we've discussed so far. If information is inherently physical and it's stored in matter, then any operation we do on that information must also have a real physical effect.
Exactly. If you want to change information, you have to change the underlying physical stuff it's stored on. Berkovec uses the example of deleting a digital photo. According to something called Landauer's principle, that actually releases a tiny bit of heat because you're rearranging electrons. Even measuring a quantum state, just looking at it changes it. And there's this thought experiments with Maxwell's demon that shows acquiring and erasing information actually costs energy and increases entropy.
So the point is, nothing is truly virtual. Every calculation, every thought has a real connection to the physical world.
Absolutely.
But now, having established this deep link between information and physics, Berkovec tackles this much trickier concept of meaning. He says physics gives us a great framework, but it can't fully explain how information actually becomes meaningful to us. And this is where he introduces these ideas of recursive and fractal models.
Yeah.
How do you see these models bridging the gap between information and meaning?
Well, it seems like he's suggesting that the way fractals work, encoding their history and being unpredictable, is kind of like how information gains meaning through repeated interactions in different contexts. Recursion, where you define something in terms of itself, and fractals, with their self-similar patterns, they give us a way to understand these complex interactions and how meaning emerges.
He points out that even a small part of a fractal contains the history of how the whole thing was generated. And similarly, information gets its meaning through all these layers of interaction. You've got historical context, environmental influences, what we already know, our intentions. It all adds up.
Right. And just like tiny changes at the beginning of a fractal can lead to huge differences in the end, little differences in information can have big impacts in the real world.
To formalize this, Berkovec brings back an equation we saw in the productive edge. Next state equals F previous state context.
Right. And he reminds us that state in this equation includes all the relevant information patterns. That's both internal stuff, like what's going on inside an AI or our own minds, and external stuff, like what's happening in the environment or what happened in the past.
Okay, and context is all the external information, all the matter and energy that could affect the state. That includes past interactions and even what we expect will happen in the future. His key point here is that meaning isn't fixed. It's constantly evolving through these recursive interactions. Every decision, every thought, every interaction creates a new context that shapes how we interpret future states. He uses some really cool examples to show what he means, like a pilot setting a course for a plane. That one initial action sets off a whole chain of interactions, adjustments to the navigation, communication with air traffic control, the actual path the plane takes. Physics explains how the plane moves, but to understand why the pilot chose that route and what it means, we need to think about it recursively.
Makes sense.
Another powerful example is human conversation. Something as simple as saying welcome versus saying go away can change the entire course of relationships or even whole societies. From a purely physical point of view, they're just sound waves. But the impact they have on future interactions and the meanings that emerge are totally different.
Right.
And of course, he talks about AI, where small changes in the data or the prompts can lead to huge differences in the output because of this recursive amplification effect. What do you see as the biggest implication of this recursive framework?
Well, Berkovec outlines several important consequences. One is that it makes systems really sensitive to initial conditions. Just like with fractals, tiny differences in information can get blown up over time, which makes predicting what will happen in complex systems very difficult. And this leads to inherent unpredictability. Because these recursive systems are so nonlinear, even a small change can have a huge and unexpected effect. Meaning isn't something you can always figure out just by looking at the starting conditions.
It's not all about unpredictability, though. He also talks about increasing coherence. As these recursive processes play out, the system incorporates previous states and contexts, and its internal structure becomes more refined. The information patterns become more interconnected and organized over time.
Right, and this drives the emergence of complexity. New structures and patterns arise spontaneously from simpler starting points through this layering of information.
And the role of memory, which we talked about earlier, becomes crucial here. Memory allows these recursive systems to hold onto and build upon information states. Complexity becomes cumulative, and this fosters something he calls adaptive intentionality. Through repeated interactions, systems can get better at aligning themselves with their goals and with their environment.
Right.
And here's a really interesting connection he makes. Because of this fundamental link between information and matter, the increasing coherence of information actually translates into increasing physical organization and complexity in the material world.
Exactly. He gives examples like biological evolution, where recursive genetic processes lead to more and more complex life forms, or how learning in neural networks actually physically rewires the brain, and even technological progress where we keep refining computers and making more sophisticated microchips. It all fits this pattern. He even suggests that these recursive interactions might be like fundamental engines of order in the universe, working against the tendency towards entropy.
Which leads us to the question of entropy, right? The second law of thermodynamics says that entropy tends to increase in closed systems. So how does that fit with this idea of recursion creating order?
That's a great point. Berkovec addresses this apparent conflict. He says that while recursion can create order locally, truly complex structures tend to arise in open systems, systems that exchange energy and entropy with their environment, like living organisms or technological systems.
And that's where he brings back the concept of the productive edge from his earlier work. It's that sweet spot between being too rigid and predictable, which is low entropy, and being too random and chaotic, which is high entropy.
Right. The productive edge is where chaos meets order. It's where new patterns and structures can emerge. And he argues that this principle governs how the ordering tendencies of recursion interact with the disordering tendencies of thermodynamics.
Okay, so let's loop back to the productive edge and how it applies specifically to large language models, which is what we focused on in our last discussion.
As we discussed, LLMs at their core are deterministic. They follow rules. But their output can be surprisingly unpredictable. Berkovec suggests that this is because they're operating close to this productive edge, where you have this fractal-like recursion, the limitations of their context window, and some element of randomness all coming together.
Right, we talked about how, even though the underlying mechanism is just matrix multiplication, the fact that they amplify small changes, use random sampling, and feed their own output back in makes them unpredictable. It's like those iterative maps in chaos theory where simple rules can lead to very complex behavior.
And just like the Mandelbrot set has those areas that are bounded, unbounded, and that in between the edge region, LLMs seem to show similar behavior. They can produce predictable outputs, nonsensical outputs, and then those really interesting outputs that seem creative and emergent. Berkovec reminds us of those four characteristics of fractals we talked about: sensitivity to initial conditions, self-similarity, recursive feedback, and emergent complexity. We see all of those in LLMs.
And he even brings back the A-B experiment, where the LLM is told to always respond B to A, but eventually breaks the pattern. It suggests they're capable of more than just following instructions. And that self-referential naming prompt, where it keeps refining its suggestions to come up with seemingly more unique names, shows this recursive, fractal-like process at work.
Right.
The implications for AI research, like he emphasized in his earlier article, are still huge. It highlights this tension between wanting coherent output and wanting those unexpected breakthroughs. And it shows how difficult it is to control these unpredictable emergent behaviors. And it points towards using mathematical models from chaos theory to better understand these systems.
Yeah, I agree.
So to wrap up this deep dive, I think the core insights from Every Bit Matters really build upon what we discussed in the productive edge. Every digital bit has a real physical impact. Information and matter are deeply intertwined. and meaning emerges through these recursive interactions. And the productive edge gives us a valuable way of thinking about the balance between order and chaos in complex systems, whether that's AI or the universe as a whole.
Absolutely, and Berkovec ends his article with a powerful statement that sums it all up. Every bit matters, every thought matters, every choice reshapes the world. It's a reminder that information, even at its most basic level, has a profound impact on the physical world and on the meaning we create.
It really makes you think. If every interaction we have online, every thought we have, every choice we make is actually reshaping reality on some way, then what does that mean for us? What are our responsibilities? What are the possibilities? It's almost like we're actively shaping the universe through our everyday actions in this digital age. It's definitely something worth pondering. Thanks for joining us for this deep dive.